Let us solve one numerical on your eccentric axial loading. We already see in our earlier discussion that eccentric axial load is equivalent to one axial load and one constant bending moment. So you can replace a eccentric axial load with the axial load and a constant bending moment, and with the help of the normal stress and the bending equation you will be able to calculate the bending stresses and normal stresses induced in that beam. So let us solve an example for this. We have this bar. Let us say this is the bar which is given to us. It is a rectangular bar, and this is the cross section of this bar, in which this width will be given as 50 mm and this depth will be given as 100 mm. So there is a load which is acting at this point. That load is a compressive load, and I can say that this is a load of 10 kilonewton is applied on this bar. So this load is a eccentric axial load, because if you see, this is the member, so this is the longitudinal axis. So if I say that, suppose this is the member, right? So this is the cross section. In the cross section we are saying this is x-axis, cross sectional axis is x-axis, this is y-axis, this is y-axis, and this one is your z-axis, this is z-axis. So the z-axis is your, what we can say, a longitudinal axis, right? So this is your longitudinal axis, and the load P is perpendicular to the cross section, parallel to the longitudinal axis, but it will not pass through the longitudinal axis. So we can say that the load P is a eccentric axial load, and the eccentricity, that means the distance from this point to the neutral axis, is given as your 10 mm, right? Is given as your 10 mm. So we have to find what is the maximum stress induced in this bar, right? We have to find what is the maximum stress induced in this bar and where this maximum stress is induced, right? We have to find where this maximum stress is induced because of this load P, that is 10 kilonewton. So we can say that earlier also we know that one eccentric axial load will be equal to one axial load and one constant bending moment. So if I replace, we know the procedures how to replace it. I am just applying two equal and opposite loads at this neutral axis, right? I am applying two loads, that is P1 and P2, on this axis, such that we can say that P1 will be equal to P2 and it will be equal to P, that is 10 kilonewton. So this P1 and P2 are equal and opposite, so the net effect of P1 and P2 is 0, hence the bar is still under the load P. So I can say that in this case, if you see that this P2 will be a axial load. How axial? It is perpendicular to cross section and parallel to the longitudinal axis and pass through it. So P2 will be a axial load, and which axial load? It is compressive axial load, right? So because of this P2 we have compressive normal stress. We have compressive normal stress on all the fibers. So if I write here that this is the P2, this is P2, which is a axial load, right? Which is a axial load, and because of this P2, that is a axial load, this member is under the compressive axial stress. So this fiber of the member is also under compressive, that is minus sigma axial. Why minus? Again I am saying why minus, because it is a compressive stress and we are taking our sign convention as compressive as negative, tensile as positive. so it is minus axial. This fiber is also under stress, that is minus sigma axial, and the same stress is at this fiber, that is minus sigma axial, right? So this is because of the load P2. This is because of the load P2. So if I say that load, now this P2 is gone, what is left with us is P1 and P. So this load P1 and P, this P1 and P will be equal and opposite forces, but at a distance between them is some eccentricity, let us say E, which is 10 mm. So this P and P1 will give us a bending moment in this direction, right? If this P and P1 will give us a bending moment in this direction, so this will give us a bending moment which is a constant bending moment, and the value of this bending moment is load P into eccentricity E, right? So it will give us a bending moment in this direction, so I can say it will give us a bending moment in this direction. The value is P into E, right? It will bend it like this, right? Now if it will try to bend this object in this condition like this, I can say this is the bar, so at this point the bending moment is like this, right? At this point the bending moment is like this, so there would be a reaction on this. Because of this fixed member will give you a reaction in the opposite direction like this. The reactant, your reaction bending moment, which is also equal to P into E, and a reaction compressive load, that is P, right? This is the reactions. These are the reactions, because every action is equal to a reaction which is of opposite nature, right? Because of opposite sign. We can say, so these will try to bend this in this direction. These bending moments will try to bend the bar in this direction. So if I draw here that this beam will have a tendency to bend like this, right? This beam will have a tendency to bend like this because of this bending moments. So if it is bending like this, then the fiber on the left hand side is under tension, the fiber on the right hand side is under compression. So you can say that the sigma on right hand side, sigma because this is a bending moment and bending moment is a normal stress, we already see. So sigma on right hand side because of bending is compressive, and you can say sigma on right hand side, left hand side of the left hand side fiber because of bending is tensile, So we can say that the bending stress here is minus sigma bending for right hand side, and here the bending stress is plus. Why plus? Because it is of tensile nature, sigma bending for left hand side, right? For left hand side. So if you say that the stresses, this is the stress, right? We calculate the stresses on each of these fibers because of this eccentric axial loading, which is equivalent to one axial load, one constant bending moment. So if you see in this diagram, we can say that the total stress on left hand side will be minus sigma A plus sigma B. The total stress on right hand side is minus sigma A minus sigma B, right? This is minus sigma A minus sigma B. So if you can say the maximum stress is on the right hand side figure. We have to find maximum stress. It may be compressive, it may be tensile. So we can say that because the magnitude of sigma maximum is at right hand side, because it is minus minus and this is minus plus. So the net magnitude will be maximum for the right hand side of fiber. So we can say that the maximum stress will be equal to minus sigma A minus sigma B. Sigma A is axial stress, is load per unit area, that is P upon A, and bending stress is M upon Z, that is My upon Zy. Why? Now you have to understand this. In the plane of cross section we have two axes, y axis and x axis, right? This is the bar, this axis is Z, this is x, and this axis is y. If you rotate this, what you will get is x and y, right? Again you will see again, this is z axis, this axis in the plane of cross section is x, and this inner axis is y. So if you rotate this like this, so this axis is y and this axis is x. So I write here, this is x and this axis is y. So y axis is this one. Now I am bending it like this, right? Now this bending moment will try to bend the beam in this plane, right? In this plane, in this front plane. The bending moment will be like this. So the bending moment will be in this plane, and this bending couple will be about this inner axis, that is y. The axis about which a couple is acting is the most important thing, because you have to calculate the moment of inertia and y max. This is the most important thing, right? So please understand how to find which axis we have to take. The bending is in this plane, in this front plane, because they will try to bend it in this plane. So the couple is in this plane, and this plane couple is around this inner axis, that is the y. So that's why I am writing here that bending couple is along the y axis, and we have to take the polar moment of inertia around, section modulus around y axis. So the section modulus will be equal to moment of inertia about y axis divided by the distance of the topmost fiber or the farthest fiber, the fiber which is at the more distance, right? If you can say, we'll discuss it later also, but the bending moment is acting about this y. So the y max is the distance from this axis to the farthest, which fiber is far, that distance we have to take. So it is a symmetrical body, so this distance is also 50 meter and this distance is also 50 meter. So this is the y max, this is y max, right? And what is the polar moment of inertia about y axis? About y axis, polar moment of inertia for a moment of inertia for a rectangle is about y axis is this dimension b d cube upon 12. What is the moment of inertia about x axis? Is this dimension d b cube upon 12, right? So I can write, I have to find the moment of inertia about yy. So about yy it is b d cube upon 12. So to remember, how to remember? If you can say this is a rectangle, this is a rectangle, this is the width b, this is depth, or you can say this is width b, this is depth d, and you have two axes. Let us say this is x and this is y. How to remember is Iyy is equal to, if you want to find this, the dimension which is cut by this axis, the dimension, there are two dimensions b and d, the dimensions which is cut by this axis is b. So the moment of inertia is d, the dimension which is cut by the y, by the x is the cube of this bd cube upon db cube upon 12. Ixx, if you want to calculate, xx is this one, the dimension cut by this axis is d, so d cube, next dimension is b upon 12. This is how you can remember how to calculate the moment of inertia about x-axis and y-axis in the case of rectangle. The dimensions which is cut by the axis, you have to take the cube of that dimension, other dimension will remain same upon 12. Right, this is how you can remember this. So this is 1 by 12 BD cube upon y max is d by 2, this half distance. We'll see later on what is the meaning of y max, how to calculate the y max, but just for the understanding I am just writing down it is d by 2 in this case. So if you put the value, you can calculate the maximum stress, maximum normal stress will be minus 3.2 megapascal, and it is of compressive nature. It is of compressive nature, right? So this is how you can solve the numerical based on your eccentric axial loading. Now, as a form of shortcuts, if you want to just to identify, just this is for your engineering services, this is for your conventional approach. This we can do as a conventional approach, but in GATE exam the most important is your time management, how to just identify that at which fiber the stress will be maximum and just do the calculations. There is a shortcut for this also, right? If you find that this question is asked in GATE, so just remember one thing, the fiber which is close to the point of loading has the maximum stress, right? Again I am saying the fiber which is close to, which is near to the point of loading, point of eccentric axial load has the maximum stress. If I would say that, suppose you have the case like this, just for the shortcuts I am just telling you how to remember the things, how to make questions fast. Suppose this is a bar, this is a longitudinal axis. If I say that I applied a tensile load here, P, I applied a tensile load here, right? So this is a eccentric axial load. You know that how to solve this. Just introduce two equal and opposite loads here. Just make the equivalent diagram and solve for it. For the shortcuts, you know that this is axial, this is tensile load. So if you make this P1 and P2, you say that this P1 is a axial load which is tensile nature, and this P2 and P will give you a bending moment. That is the case for your subjective. For your objective, if this is a tensile load, then sigma axial will be of tensile, right? Sigma axial will be of tensile, that is plus, if it is a tensile load. And you know that, just remember one thing, the fiber or the section which is close to the point of loading, close to the point of loading has maximum stress, So the fiber which is close to this P is this bottom fiber, this top fiber is far from this point, this is the point of loading. So we know that at this bottom fiber stress would be maximum, right? Stress would be maximum. So I can say that if the stress is maximum, you have to now superimpose the bending stresses. And you know that on one fiber bending stress is compressive and on another fiber bending stress is tensile, right? We know that bending stress on any one of these fiber will be tensile and the other fiber will be compressive. But we know here the total stress will be maximum. So this is plus. For the maximum you have to add the bending stress, right? You have to add the bending stress, then only the magnitude of this will be maximum. So this will be minus sigma b. No need to go for this complete discussion, just make sure if I solve for this like this is the case, right? If I apply a compressive load here, compressive eccentric load here, so because of compressive axial load, the axial stress would be compressive, that is minus sigma A, right? And now we have to superimpose your bending stress. So we know that bending stress is, one is tensile, one is compressive. This is the point of loading. So the top fiber is near to the point of loading. Top fiber is near to the point of loading. So we can say that if the top fiber is near to point of loading, then the stress on the top fiber will be maximum. So if this is minus and you need a maximum, then you have to take minus sigma b, and this will be plus sigma b. You can cross check it by using this method also. This is a shortcut how you can solve it, right? So if I say, for one example also we can take, just for your better understanding, this is the case, and I apply one eccentric axial load here, right? Eccentric axial load here, which is of tensile nature. Because it is tensile, so sigma axial will be plus tensile. Now we can say that we have to superimpose the bending stresses. One bending stress is positive, one is negative. This is the point of load. So the top fiber is near to the point of application, bottom fiber is far away. So the stress on top fiber will be more than this. Now we have to superimpose bending. This is plus, so you have to add bending, and here you can subtract. We know one is positive, one is negative. So maximum stress means maximum magnitude. If compression is minus, so you have to take minus sigma b, and if it is a tensile, then you have to add plus sigma b. On the other fiber it would be minus sigma b. This is the way you can solve the question very easily in your GATE exam if it comes, or in case of your engineering services or any conventional exam, you have to go for this complete detailed discussion how you can take this minus sigma a and plus sigma b. Then you have to explain it like this.